Welcome to Careless Coder, and today we will be creating a 32-bit I/O that you can connect to your Raspberry Pi or Arduino or even Commodore 64 if you want to bit bang it. It is all SMD. I created this PCB and I'm going to teach you how to make this ghetto style. Motherfucker! So the heart of this design is this MCP 23017. I got two of them, and this is a 16-bit general purpose I/O extender. It works over I2C, your SDA and your SD clock. The reset needs to be pulled high, and you can put 8 of these on the same bus. So this one is set to 0, which effectively makes it address 20, which is a bit weird because the highest nibble is already programmed. And this is set to 1, so basically becomes address 21 on your I2C bus. Then we have some current limiting resistors and the individual LEDs and the headers. These headers are there that you can put your inputs on. So we have one going to ground, and then you have these 8 pins that you can put your inputs on, which is cool because then also the LED will light up according to what you input. And you can also read this from the system. You basically connect it from this header. You have the VCC, the SDC, the SDA, the SDC and the ground. But I also added this diode and this DC jack. Bear in mind, this again is inverted because, like I said last time, I have many of these adapters that have the ground on the inside and the plus on the jacket. So that's why I wire this. But you can of course flip it up, and I will put this on the GitHub as well so you can change your design. Then we go to the PCB because it's all about creating SMD workflow. So here we have the SOT package of the two MCP 23017s, the pull-up resistors. These are all 1601 form factors. These are very easily to solder also by hand. And this is the DC jack and that diode. By the way, if you connect this to a Commodore 64, that's why I have this DC jack, then you don't connect the VCC here. Then you just connect the VCC here. You can connect the ground, of course, you need to do that, and 2 pins of your user port to bit bang it. And those are the headers that you can put headers on, or just solder the wires if you need any input. And of course, these are optional. If you just want to use the I/O on the headers, you don't need to solder these. So let's jump in and make it. I use a lead-based solder paste that melts at 183 degrees centigrade. I did notice that according to my thermometer it melts already at around 150. Here I draw a little stripe over all the pads, and then I place the IC on there. These are candidates for bridging, but that's easy to fix. Then for the 1601 components, I tap the pads 2 or 3 times to get a small little dollop on there. It's easy to overdo it, less is more. Because according to the spec sheet, this only needs 42 microns to cover a pad. So when you just put it on there with a little tab, then you already have enough. Sometimes if you overshoot it, you take some alcohol and you just wipe it off and you start again. It's easier to redo it than to have too much solder on there and have to fix bridging. There's always a little bit of fixing going on, but that's not really difficult if you use a reflow. Here I put the resistors, then I put the LEDs. Be sure to notice that these have a polarity, and you need to check for each LED that you buy what the right polarity is, because there is no standardization. So here's the board, I chuck it in the oven. This is completely unmodified. You see the temperature probe in there. I turn it to 150 degrees centigrade and I watch it warm up. When it goes a bit slow, I increase the heat a bit more. And the reason I set it to 150 is that I know that when it reaches it, I see it reflow. And that's knowledge that I've gained from doing a little test. Now I turn off the oven and let it cool down.
So we got a few things to fix. First of all, this tombstone. Some of these LEDs aren't quite straight, so I will fix those. Even though this is not really an issue because it's a ground plane, but I would like to have them straight. Here we definitely have what I expected. Too much solder that bridged these two, so I will fix those. And I fixed this. Some tiny little bridges, but they are easy fixable by just dragging the solder iron.
So I've cleaned the IC shorts by just dragging the soldering iron with some flux. And now I'm fixing the tombstone LED. I took that off and just resoldered in place. And this was the first board. The second board just reflowed perfectly. That's the bit of experience that you get with a second board, that how much solder you need.
Okay. I think we got a clean board.
So now that the hardware was made, I needed to create a little test. First and foremost, you need to enable I2C on the Raspberry Pi. You do that by using raspberry-config. Go to interface, P5 I2C and enable that. Without it, it will not work. Then I created a little Python test program, which was based on this library. I will put this link in the description and basically set this up. Except I had to instantiate two MCPs because I have a U1 and a U2, of course, with different addresses, and then created a little pulse. Now this looks like this. So this comes from that example code. Then I created two little instances, one on address 20, which is basically when the MCP 23017 is set to 0. And 21, that's when you tie the A1 address line to VCC, and then it's set to 21. So basically the upper nibble is set to 20 for this device. Then I did a loop forever that pulses the LEDs. I get a pin, I set the output to be output, and then I set the value to true depending on the modulo. And otherwise I set it on false, and I do the reverse for the second MCP. So you get this weird pulsing LED. Now setting the output every time is a bit useless. I could have created a second loop that just set the values to output, but you know, I wanted a quick and dirty test because usually I don't use Python for my robots. I tend to use C and C++. So that was the next step. I started to create a little wrapper based on GPIO. I have three functions in this wrapper that are solely handling outputs. I tend to use outputs only on the I2C because usually I don't need very fast outputs for stepper motors, etc. And the inputs tend to be a lot faster when you read different sensors, etc. So I want to connect those as much as possible directly to the Pi, or the Arduino, because this will also work on an Arduino. Because the I2C bus is only 100 kHz, 400 kHz or 1 MHz, so it's not really that fast. On the Raspberry Pi, the default is 100 kHz, I set it to 400 kHz, and that's the maximum. So what do these three convenience methods do? Well, set GPIO out takes a file handle to the MCP and takes a port A or port B, because on the MCP the two different 8-bit ports are called A and B. And I will set that register to 0, means that all the bits are set to outputs. And for the register 1, that's port B, I set them to 0. Those bits are all outputs. Now you can of course set a different bit mask here, and then those bits that are set to 1 will be inputs, and those bits that are set to 0 will be outputs, but then you will create your own little function and not use this, because then this will not work. And then I have the set 32-bit value, because I don't want to deal with the 4 individual ports. I just want to pass in a 32-bit value and have that set on the 2 MCPs on my board. So I create a character that holds a byte, and I pass in that value, so I only have the bottom value left, and set that to register 14 on the first MCP, U1 basically. Then I shift it over 8 positions, and then I have the next 8 bits, so the 16 bits, set that to register 15 on U1. I shift it over 16 positions, then I have it on register 14 for U2, and shift 24 bits over, and then I have it on register 15 for U2. And then basically set the whole 32-bit value, unsigned value in one go onto the output. And this is a convenience wrapper around set GPIO, where I set both A and B for both devices to outputs. And then I created a little Knight Rider scanner, a LED scanner that we did in programming GPIO in assembler for ARM. So first I need to GPIO initialize the PIO, then we need to open the I2C bus. Now if you have an I2C bus on a Pi, you can see which one it is by, well, let's do this, because there is only one. By doing an ls, and then you see -1, and that is your device. So that is basically the one here. And then of course we pass in the value for the address for U1 and U2, and the flags are 0. Here I check if there's any issues. If there's any issues, then the value is less than 0. Then we need to stop, because the the device driver, because I also tried a low-level program myself, the device driver then doesn't allow you to send data. So here I call my convenience methods to set the 32 bits to outputs, and here I do a while loop and scan the LEDs for M1 and 2 with a time interval of 10 milliseconds per LED. And here I do it, I'm shifting over every time by 1, setting the value, sleeping. I don't even think I need this, because I don't overshoot it here. No, I shouldn't need this, but well, it's there for safety. And then we shift back to the right, set the values, sleep, and we recurse that, so then we have the LEDs going up and down. So then I figured, why not create a file that allows you to set the pattern that you want to display on the LEDs. And basically have 2 values, the timeout value and the 32-bit value that you want to set on the 32 ports. So I quickly knocked that up. So what I did is I created a vector. A vector is basically a dynamic array in C++ that holds a pair of unsigned integers, because the time is unsigned, and of course the 32-bit value is very much unsigned. I call that steps of a sequencer. I call the PIO GPIO initialize. Then I open my U1, which is still connected to device 1 on the I2C bus with flag 0. Then I connect my U2, which is still on the 1 and never going to change on the Raspberry Pi 4, and set the flags to 0. Then I check whether these handles are open, like I did before. If it is less than 0, then something is wrong, you cannot continue. Then I check whether the arguments are set to 0 because we need a configuration file. If it's not, I exit. Then I set all the ports to outputs with the wrapper function that I showed you before here. Back to main. Then I parse the file. So basically I take in a file name and my steps that I'm going to fill. I open a file stream and a line to hold that data. Then I check whether the file is actually open or not. If it isn't, I return -1 and we exit. If everything is alright, we return 1, so that's good. Then we read a line. Now it's not really efficient to read line by line, but these configuration files are so small. I mean, they're not going to be multiple megabytes. Otherwise you would first run to read them into a big string in memory in one go and then parse those. But now it's easy enough to parse it line by line in the stream. And I check for a space, and that is delimited in the data the first time that I call it, so we have the milliseconds. So I read that data in the stream and I stream that out so it's converted to the unsigned integer of delay. Oh, there it is. I was looking for it. Then I need to clear it, otherwise it will append or do weird things. I read the next line stream with the next token of the space. And that is actually, if you see, a hexadecimal value, because I don't want to deal with decimal or binary values. That would be too much typing. So I convert that back to decimal with just streaming to the string streamer. And streaming it out, and then it will turn it into an unsigned integer. So that's as easy as that is. And then I push back this pair that I create on the steps. Then we have all the steps in this lovely little array, or vector I should say. And then we loop through the vector infinitely, reading every time a step and setting that step to the value. This is a bit weird, the second. It's a pair, so a pair has a first value and a second value. And the second value, as you can see, that is the actual value that we put in the U1 and U2 ports. And the first value is the timeout. So could be a bit dodgy if you read second and think, hey, is that the milliseconds? No, it is not. The milliseconds is in the first part of the pair. And we multiply that by 1000, so we have microseconds. And that basically reads that file and just plays back what is in there. Very, very simply. So there you have it, a very simple way to create your own SMD PCBs in an unmodified toaster oven. There's no need to modify your toaster oven. You can just write the temperature manually and have the similar results. It's just that easy. And SMD is really nothing to be afraid of. It's easy even to solder it by hand, but the toaster oven just makes it so quickly. So I hope you learned something and see you in the next one.